We're just going to add a few other topics to our discussion of Fourier series to help sort of wrap things up. First, we'll look at a couple of examples, and these are going to be two examples involving what we call rectifiers. You might find them in a power supply, such as you use to charge your phone or your laptop, for instance. And we'll look not only at the use of Fourier series in analyzing these things, but also at frequency response. After all, we motivated Fourier series by saying that would let us extend our frequency response analysis methods to other periodic signals. So that's exactly what we'll do in these examples. Then we'll come back to the issue of convergence, and we'll talk a little bit more about the manner in which Fourier series converge in the neighborhood of discontinuities. This involves a phenomenon called Gibbs phenomenon, so that'll probably be our last topic on Fourier series. So we're going to start with what's called a half-wave rectifier. So a rectifier is a device that you use at least in one stage of the conversion of an AC voltage, a sinusoidal voltage, into a DC voltage. So a so-called half-wave rectifier might have a circuit diagram that looks like this. Here we have our AC voltage, so let's say it's A sine omega t. There we have a diode, and you can think of a diode as a device that only lets current flow in one way, namely in this direction in which the triangle is pointing. For a load, let's just add a resistor across the terminals here, and we'll have an output voltage here. So because this diode only lets current flow from left to right, through it from left to right, it's only when this alternating voltage has, if you like, positive polarity and is applying a positive voltage between this terminal and this terminal, that it will allow current to flow and will therefore produce a non-zero output voltage. So if we feed in this A sine omega t at the input of our rectifier, V out of t, our output voltage, will look something like this. As long as the input voltage is positive, it will essentially pass right through and show up at the output. So for the first half period of our sine, we'll have a positive voltage. We'll have half of a sine wave, if you like. Probably draw that a little better. So this will have the amplitude A, but when the voltage at the input becomes negative, then this diode will be biased in the reverse direction. Current will be trying to flow through this way, but the diode does not allow that. And for that reason, it'll function essentially like an open circuit, and we'll just see zero voltage here at the output. So for the next half period, we'll just have zero voltage. Then when the input voltage becomes positive again, it will again be passed and show up at the output. So in this way, our sinusoid becomes unipolar, if you like, and the voltage at the output is non-negative. So this is one step in converting our alternating voltage into a DC voltage. We would have to do a lot more to clean this up to make it a nice steady DC voltage. And one way we can analyze this signal and see exactly what we need to do to it is to find its Fourier series. Right, this is a periodic function, so we can find its Fourier series. Now, I won't go through the calculation. The details are given in lecture notes, part 5C. And it's not difficult. We're just dealing with exponentials here, so it's just a matter of integrating exponentials. What we find is that for n not equal to plus or minus 1, the Fourier series coefficient C sub n is going to be a over 2 pi times 1 plus minus 1 to the n over 1 minus n squared. When n is equal to 1, you get C sub n equals a over 4j. So this will be, if you like, the coefficient for the fundamental frequency. And similarly for n equals minus 1, we get that C sub n equals minus a over 4j. Again, this, if you like, is at the fundamental frequency. This is the coefficient of the complex sinusoid whose period is the same as that of our original sinusoidal voltage. And finally, we have the component that we're really after. If we're trying to create a DC signal, then the nice part about what we get at the output is the DC component. Represented by C0. So you can go ahead and compute these Fourier series coefficients if you like. It's a simple exercise in finding Fourier series. And what we're really after in this case, since we're building a rectifier, is this DC component. So you see here that we had a sinusoidal input whose amplitude was A. The DC component of our half-wave rectified output is A over pi. So we've decreased, if you like, we've gone from an AC voltage with an amplitude of A to a DC component that is only A over pi. And obviously we'd like to get rid of all of the sinusoidal components, ideally, if we're trying to build say a DC power supply. So the most troublesome of these sinusoidal components will be the lowest frequency one, because we'd like to keep the DC component but get rid of all the sinusoidal components. So the one whose frequency is closest to 0 is the fundamental component. So the component at the frequency of the input is given by our C1 and C minus 1 coefficients. So this works out to be A over 4j. C1 is A over 4j. C minus 1 is minus A over 4j. So we get A over 4j times e to the j omega t minus e to the minus j omega t. And of course this difference in these complex conjugate complex sinusoids is going to be a sinusoid. This will give us 2j sine omega t, where omega is 2 pi over capital T. And therefore what we have is A over 2 sine omega t. So this is the lowest frequency sinusoidal component. So what we'd like to do ideally is to pass this through a system that will let the DC component through, ideally without any attenuation, without any decrease in its amplitude, if you like, but that will decrease the amplitude of this sinusoid and all of the higher frequency sinusoid. And note that this most troublesome of these sinusoidal components is exactly 1/2 of the input sinusoid. Now, we're not going to go ahead and try to do this filtering. In fact, maybe I'll just say, I'll just give the whole Fourier series. Again, you can work out the details for yourselves or check the details in chapter 5c of the lecture notes. We have this DC component at A over pi. We have this component at the fundamental frequency that's exactly half the input sinusoid. This first one comes from n equals 0. This next one comes from setting n equal to plus or minus 1, as we saw. And then the rest, for n not equal to plus or minus 1 and n not equal to 0, works out to be the sum from n equals 2 to infinity of 1 over n squared minus 1 times the cosine of omega nt. And this is just for n even. Okay, so we've got the DC component that we're after, and then we've got sinusoidal components, the lowest frequency one just being exactly half of the input voltage. So it turns out that we can do better than this if we use a so-called full wave rectifier. So we're going to leave this here for now, and we'll analyze a full wave rectifier, and we'll see that it gives us a Fourier series that looks a lot more promising from the point of view of building a DC power supply. So what's a full wave rectifier? Well, it's essentially two half-wave rectifiers put together. Let's take the same input voltage and let's have our ideal diode that we had last time. And our resistor. And we'll make things symmetrical by adding another ideal diode in the return path here. So at this point, we've got essentially the same circuit as before. This is essentially just a half-wave rectifier. So we know this will give us the positive part of, or the non-negative part of the sinusoid, if you like. But we'd like to use both parts. So we're just going to connect another half-wave rectifier by taking another diode, connecting it to the other side of the input voltage. And leave more room for another diode. And we'll do the same thing over here. Oops, this goes the other direction. So here I've added just another half-wave rectifier that's hooked up the other way. So it will give us a positive voltage on these terminals when our input voltage is negative. Okay? So it's really just two half-wave rectifiers put together. And the output waveform that this will give us will look like this. Let's again call this output voltage V out. So during the first half period, it's going to give us exactly the same waveform because it's going to be using this half-wave rectifier that we've got here, composed of those two diodes. So we'll get exactly this sort of half of a sinusoidal waveform that we saw before. But then when the input voltage goes negative, these diodes are essentially just going to shut off. They'll be biased in the wrong direction, so they just won't allow any current through. However, these two will. And because they crisscross like this, when the input voltage is negative, that will give us a positive voltage at the output. So we'll just get another one of these half sinusoids for the next half period. And so on. So intuitively this looks a lot better. This gets us closer to the DC voltage that we would like to have. Okay. So we can again compute a Fourier series for this nice periodic waveform, and we'll be able to see immediately from the coefficients that this will give us a much better head start when we're looking to build a DC power supply. What do we find in this case when we compute the Fourier series coefficients? For n not equal to plus or minus 1, and I should also say for n not equal to 0, what we end up with is Cn equals minus a over pi times 1 plus minus 1 to the n times 1 over n squared minus 1, which looks a bit like what we had before. Actually, this does apply also for n equals 0, so let me leave that out. So in particular, for n equals 0, C0 will be minus a over pi times 2. The expression in square brackets works out to be 2 times 1 over minus 1. So we end up with 2a over pi. So just as your intuition might suggest, the constant component of the Fourier series has twice the value that it did in the case of the half-wave rectifier. So this gives us a much bigger DC component, twice as big. Now, what if n is equal to 1 or minus 1? Well, if you go through the calculation, as is done in the notes, I won't go through it, I won't repeat it here, you just find that C1 equals 0. And similarly, C minus 1 equals 0. And this makes a certain amount of intuitive sense, because if you look at the period of this signal, it has a period that is half that of the input signal. So the lowest frequency sinusoidal component is going to have twice the frequency of the input signal. We won't have any component that has the same frequency as the input signal. And that's another big advantage if we're trying to build a DC power supply. We want to get rid of any sinusoidal components, and now the lowest frequency sinusoidal component that we have to deal with is at twice the frequency of that which we had in the case of the half-wave rectifier. So in this case, our Fourier series is 2a over pi plus this sum of sinusoidal components, Cn well, I'll just go straight to the final result. The details again are given in the notes. This gives you 4a over pi times 1 over n squared minus 1 cosine omega n t. And here again just summing over even values of n. So this gives us twice the DC component, and no component at the frequency omega radians per second. The lowest frequency sinusoidal component that we have to worry about is at twice that frequency, and that's going to make it easier to filter out these sinusoidal components. Another way of comparing the half-wave rectifier with the full-wave rectifier is to use Parseval's theorem, which essentially says that we get the total power in the signal, the total average power in the signal, if we add up the average power in all of the components of our Fourier series. So let's compare our half-wave rectifier and our full-wave rectifier. First of all, the total average power in the V out That's going to be a squared over 4 in the case of the half-wave rectifier, right? Because we saw that the power in the input sinusoid itself is going to be a squared over 2. It's 1/2 a squared. We saw that that was the power of a real sinusoid of amplitude a. So with the half-wave rectifier, you are, as you would expect, just getting half of that average power, so you get a squared over 4. Whereas with the full-wave rectifier, you get all of the power of the input sinusoid. Then what do we get if we break it up according to frequencies? Okay, at DC, in the case of the half-wave rectifier, we had a DC component of A over pi. So the average power in that DC signal will just be the square of that voltage, A squared over pi squared. With the half-wave rectifier, we had twice that DC component. So when we square that to get average power, we will get, to get the power in the DC component, we'll get 4 times what we had in the case of the half-wave rectifier. What happens at the frequency of the input voltage? In the case of the half-wave rectifier, the power of that component will be a squared over 8, 1/2 a over 2 squared, because the amplitude of this component in the case of the half-wave rectifier was a over 2. So 1/2, that amplitude squared is a squared over 8. And then in the case of the full-wave rectifier, we didn't have any component at the frequency of the input signal. And then in all of the other components, we know that what we will get is simply the total power in V out of t minus the power in these first 2 components. So if we take a squared over 4 and subtract these 2 components, well, first of all, subtracting a squared over 8, we'll change this a squared over 4 into an a squared over 8, and then we'll also have to subtract off this a squared over pi squared. So in all of the other components combined, we'll have a squared over 8 minus a squared over pi squared as the average power in all of those components put together. And in the case of the full-wave rectifier, we'll have the total average power of V out of t minus the power in the DC component, which is 4a squared over pi squared. So this last column we just compute using Parseval's theorem. So again, we see that the full-wave rectifier looks much better. We get much more power in the DC component. We don't get any power at the frequency of the input signal, only at higher frequencies. So this promises to make a much better DC power supply. All we'll have to do with this full-wave rectifier is find a way of preserving this DC component while getting rid of or greatly attenuating these sinusoidal components. So by attenuation, I mean the opposite of amplification. We want to make these sinusoidal components smaller while hanging on to this DC component. So we can see how to do that by using our knowledge of frequency responses. And that's what we'll do in the next lecture. See you there.